So this video provides some background and overview of assessment methods that could be used for doing TMDL analysis, watershed analysis, watershed impairment analysis. The objectives of assessment are to determine the characteristics of one or more pollutants, to determine how much reduction in load is necessary to meet water quality constraints, to identify categories of pollutant sources or even identify individual sources of a particular pollutant, to estimate how much of a pollutant load originates from each of the identified source categories or even pinpoint sources. So for instance, here maybe a point or a source category could be confined animal operations, let's say. So then you might, within that category, want to identify which confined animal operation is causing the main problem. Another objective is to estimate the improvement in water quality that would ensue from implementation of BMPs, and this basically requires that one come up with some way of assessing the change in water quality that will occur when a BMP is put in place. And that's usually done prior to actually implementing the BMP. So whatever you come up with there is going to be an estimate of the response of the system to that BMP. So what assessment method should you use? Of course, what we want to do is try to keep it as simple as possible. That's usually the best advice that one can take. Keep the method simple. The method needs to be supported by the information that's available or information that can be obtained for the location. You don't want to use a model, for instance, that requires lots of data that aren't available, because then you're not going to be able to come up with good estimates of the system response. The method needs to be understandable by the stakeholder community, because if it's not, the stakeholder community will not appreciate a presentation of the method and will not trust the results. And of course, the method should be user-friendly. So whoever's doing the analysis, you don't want to spend a whole lot of time trying to figure out how to use the method. It should be something that's fairly straightforward to use. So here I've identified two categories of methods, two main categories of methods. And after I've described these two methods later, I will go through some other methods which maybe actually should be included as other categories, but I don't really do that in the presentation. So the two categories are category one, which is methods that are based on monitoring data or literature values. So these are data-driven methods, or they are methods that depend on some published guidelines that allow one to calculate the effect of a particular land use on downstream loading. So here with these methods, the big interest is in calculating a load from a watershed or from an area, land use area. It will not generally, these methods do not provide details of what's going on within a watershed. They will provide an estimate of the load coming out of the watershed, and all the details are kind of lost in the analysis. And then for this, generally you need to have detailed flow and pollutant concentration data. The second category of methods are based on watershed scale modeling. Most of the models that we would consider for this kind of analysis will provide some details of what's happening inside of a watershed. There are many models that are available. They range in complexity from simple spreadsheet models to models that require significant computing power. And in this presentation, I will be talking about different categories of different types of models that range from very simple to very complicated. So for category 1 methods, these depend entirely on monitored flow and pollutant concentration records. In most instances, the flow sampling is continuous, but almost always the pollutant sampling is not continuous. There will be grab samples. I think that as sensor techniques improve, cost of sensors goes down, one will be able to measure pollutant concentrations much more in real time, just as flow is being sampled currently. An example of such a sensor would be the YSI probe that can measure things such as turbidity, nitrate concentration, pH, temperature, of course, and things like that. So one does not have to be in the field taking samples. One can actually monitor some of these things continuously. But a pollutant like phosphorus, you really need to analyze using by taking grab samples. When the flow and pollutant sampling are both continuous, the development of load relations are fairly easy. We'll see later that in our analysis of load duration curves that generally we do not have continuous pollutant sampling, so then there's some uncertainty in the load estimation. So the last note here is that when flow is continuous but pollutant sampling is periodic or event-based, statistical methods have to be used to develop the load relations and to come up with estimates of the load. And that's essentially what we see with the load duration curve approach. Category 1 methods are useful for determining the current or historical loads. We're quantifying loading from a watershed on a per unit basis or per acre basis, for instance. You can compare one watershed to another watershed in the same area or region in terms of the pollutant load that's coming from the watershed. You can look at the impact that existing load conditions have on downstream receiving waters. So, for instance, you could have a watershed that has a stream that's got pollutants in it, and that that stream may be discharging into a reservoir or a lake, and you may want to see what effect that pollutant load from that stream has on the quality of water in the lake or the reservoir. And these methods cannot be directly applied to determine the effect of changes in land use within the watershed. They can be used to guide one to determine what changes you might make to improve the quality of the water coming out of the watershed. But because they're statistical sample-based methods, well, you don't actually have samples from future conditions, so it's not possible to come up with estimates of future conditions. You can only estimate what the effect will be by improving conditions upstream. These methods do not provide information on individual sources of pollutant. They only give you an overall estimate of load coming from an area. And whatever scale you're monitoring at will be the scale for the estimate of the load. So if you have an 8-digit huck and you're measuring the discharge from the 8-digit huck and also measuring phosphorus concentrations, you'll be able to estimate the load from that watershed at that scale, but you would not have any detail on where those loads are coming from or how to divide the total load up among those various potential sources within the watershed. And of course, if you want to see the effect of a BMP that has been implemented, you should try to monitor at the scale of implementation of that BMP. So, for example, if you put in some riparian buffers, saturated buffers, for instance, that would remove nitrate in a particular area of a watershed that do not cover all the riparian areas, but just some of the riparian areas. If you want to see the effect of that BMP, you should monitor upstream and downstream where the BMP is actually put. So some example category 1 methods include the low duration curve, a model called FLUX, which actually calculates a low duration curve, but it does a lot of statistical calculations that help with the analysis of quantifying loads. A model called LOADEST, which is Load Estimator, developed by USGS, which is very similar to the FLUX model. The regression of pollutant load and flow using MVUE, minimum variance unbiased estimator method. And then there could be these literature values which can be used to estimate load. An example of that would be just saying, okay, for a given agricultural operation, continuous corn operation, one can estimate what the load of phosphorus would be coming from that from a particular agricultural production area based on values that you can pull out of the literature. And you would do this sort of an estimate if you had no sample data available to you. Obviously, or maybe not quite so obvious, but basically it would be best if you have flow data and sample data at the downstream of where these land uses are, so that you can come up with measurable load rather than trying to estimate using literature values. Okay, so let's look at some of these methods. A low duration curve is one that we've discussed in class. You start off with a flow duration curve, and from the flow duration curve you can construct a low duration curve. In this case, this brown line is the target flow duration, low duration curve based on a water quality standard. In this case, it's for nitrate, and the nitrate concentration for the standard is 10 milligram per liter. The FLUX model, which is developed by the U.S. Army Corps of Engineers, is a model that takes measured flow data and grabs samples of concentration, nutrient or sediment concentration, and quantifies the loads based on some statistical methods. It was developed as a companion to the bathtub model, which is a fairly simple lake model that is used for estimating the impact of pollutant loads on water quality in lakes and reservoirs. The FLUX model has, I list here 6 estimation algorithms available to it. There's actually 8 that show up when you use the model, but the 6 are the ones that are used the most often, and development of the remaining 2 is still ongoing. So basically the FLUX model will map the flow versus relationship, or the relationship between flow and concentration, and maps that over the top of a continuous flow record. So you have a relationship, for instance, between discharge and TSS that is based on sample values, and then you use that relationship with a continuous flow record to come up with estimates of the total flux of sediment or whatever the pollutant is coming out of the watershed over an annual period of time. And the nice thing about FLUX is that it gives you estimates of the errors in the estimation. It has the option to stratify the flow, or stratify the data into flow categories, and that allows you to come up with a better fit a better mapping of the sample data to the flow data. And it's partly because of the generally non-linear relationship between flow and concentration. Okay, so what it requires is that you have constituent concentrations that are collected on, it doesn't have to be on a periodic basis, but you should have data that's collected for at least 1 year. The date that it's collected is really important because you may want to stratify data based on let's say time of year. You need to have corresponding flow measurements with those constituent concentrations, and then it's you really need to have, or should have, a complete flow record as well for the period over which you want to be able to do predictions. There are these 6 algorithms that are available. As I mentioned before, there are 8, but only 6 are currently active in the model. The listing of those is not all that important right now, but I'm going to put it up here anyway. So the direct mean loading method, the flow weighted concentration method, the modified ratio estimate, the first order regression, the second order regression, and the regression applied to individually daily stream flow values. So you can use the FLUX model to come up with estimates from any one of these 6 methods. The category 1 method, called regression of pollutant load and flow, it develops regression equations that represent the relationship between pollutant load and flow, or between pollutant concentration and flow magnitude, similar to what you do with the flow duration curve and load duration curve, and also the FLUX method. This relationship is then used to predict load on days when the water quality samples are not taken, very similar to what we do with the load duration curve and with FLUX. And of course, there's usually bias in data because the water quality variables may span very large ranges. Essentially, the relationship between flow and concentration is not perfect. There might be quite a bit of variability. Anyway, so the methodology goes through and removes the bias using a log transform regression approach. The load-S method is very similar to the FLUX model as well as this RPLF model. If we don't have any flow data, we don't have any concentration data, and we want to get a first estimate of what loads might be coming from a watershed, we need to go to some other procedure. And there's a lot of literature values that have been published, tables that give the relationship between land use type and pollutant loading. Usually the pollutant loading is given in, let's say for phosphorus, it might be given in kilograms of phosphorus per acre or hectare of land area for a particular land use. Those values may be dependent on the amount of runoff that occurs, so one would first estimate the runoff, and then the literature value might give the concentration of water and chemical in runoff water, and one could then calculate what the annual load of that chemical happens to be. So you base your estimate on land use and some representative loading rate. I'll show some examples of those. Basically load per unit area. This method involves the use of export coefficients. And the export coefficients have been developed for different regional areas around the country. Those are affected by precipitation, soil type, vegetated type, the type of source activity, or where the pollutant is coming from. And hopefully you have regional values of export coefficients for the region that you're interested in working in. There's also a method that uses empirical relationships to calculate the loads, and that's based on this method called the simple model. And it is exactly that. It's a model that calculates loads based on a description of the land use type and some empirical relationship that relates runoff amount to the concentration of pollutant of interest coming from that land use type. And from that, one can then calculate the load that would be coming from that land use type. Reference for this is by Schuler, and complete reference is given here. Some idea of the export coefficients that one might use. It's given here. So as an example, for forested area, nitrate export coefficient, this is in kilograms per hectare per year, it says nothing about how much runoff is occurring, is 1.8 kilograms per hectare per year, whereas for corn, it's 11.1 kilograms per hectare per year. For phosphorus, export coefficient is 0.11 for the forested area and 2 for corn. So if one knows what a particular land use area is made up of in terms of the land use types, one could estimate how much total load is coming from the watershed or from that area. So the export coefficients can be expressed as load per area per year for a particular land use, or it could be better estimated or expressed as load per unit area per unit of runoff depth, because the amount of runoff affects how much load is going to be coming off the watershed. And so sometimes you'll find these export coefficients expressed as load per unit area per unit depth of runoff. So if you estimate how much runoff occurs, you can then come up with the load per area. Some sources for these export coefficients are given here. These are fairly old documents. Newer sources become available every once in a while, and I don't have a complete list of them here. So with that, we're going to go on and talk about Category 2 methods, but I'm going to stop this video at this point.